So what actually happened through the experiment? Well, here are the results. First it'll be useful to just review Poisson law. Pi, because there's a circle involved, r to the fourth power, and then p1, p2. And then this thingy-majiggy. And, oh, nice. I'm pretty sure that's the coefficient of friction. Oopsie, wow, I was skipping all that. Coefficient of friction. Oh, maybe it's the viscosity, either one. Viscosity? Yeah, but we're using water, so water is a pretty neutral liquid, I think. Yeah. Yeah. And then L, length of the tube. So here is what it ended up looking like. I got rid of the earplug and used tape instead, so this is actually clear, and it reminds me of a Titanic, or was it 1911, where under the ship at the very bottom there are windows sticking out, and there's a glass, and it needs to withstand a lot of pressure. So actually, if you fill this with water, you can actually see the water level through this plastic tapey window. Ooh. And I wonder if this is okay. So first idea, this, we used a phone, a stopwatch on a phone. Volume, this is not velocity, this is volume. Okay, volume. And remember that lunchbox? Yeah, basically after this tube leaked out its liquid, its contents, it would fill up the container, and then I would transfer that into some sort of measurable device, and you usually had like markings, and this is like, for example, the 100 mil mark, and this is the 200 mil mark, and usually it will lie right around here. But alas, yeah. So the first trial, it went okay. The thing with Poiseuille's law, I was trying to keep everything equal except for the radius change. Now Bernoulli's law, I'm finally spelling it right. Bernoulli's law, P1 plus rho gh or y1, it was, I like y1, h plus 1/2 of rho v squared equals v2, and then just everything except this 2 instead of 1. M, oh, I almost wrote m. So let's look at P1, P2. We're looking at these are 2 points in the container that we're talking about. Point 1, point 2. Point 1, point 2. Entrance, oopsie, entrance, whatever. And then exit. So entrance will be P1 and exit will be P2. At the entrance, what is the pressure? Well, I think if we have the top of the bottle like this, with like water filled in, at this point we have, of course, the atmospheric pressure due to oxygen and nitrogen and whatnot. That's the PATM, but I believe we also have this, wait, never mind, yeah, P1, P2. P1 atmospheric pressure, and P2, this is a pressure there. What there? It's also P atmosphere. Like the air that's squeezing around this area is about the same about as the air squeezing at this point. Like this, 2 centimeters worth of air compared to millions of miles up in the stratosphere. No. Okay. In BG1, okay, this is when physics students are like, hey, MGH, potential energy, like when you're like on top of a roller coaster and you're like, oh, this is gonna be one hell of a ride. I have a lot of nervous energy right here. Oh no, that's the potential energy. Potential energy here, and because it's Y1 height, the higher the water level, the more potential energy is going to be. If the water level is really high, it's going to be like, yeah, I get to squeeze all this water out. But if the water level is just a little bit above, then it's like, life is boring. So the challenge is I need to keep this potential energy the same.